Welcome to the Deep Dive, where we take a stack of dense sources, cut through the noise, and deliver the knowledge you need fast. Today, we're going to dive deep into a technology that has completely changed how we think about digital trust. Blockchain. It's a term you hear everywhere, right? And it's almost always tied to cryptocurrencies. But the beginner's guides we looked at, well, they show that association barely scratches the surface of what it can really do.
That's absolutely true. Our mission for you today is pretty simple, actually. We want you to walk away with a real functional understanding of how this distributed ledger technology works. We're going to map out its three foundational pillars. Then we'll walk through the cryptographic process that makes it so secure, look at its really diverse use cases, and this is critical. We'll examine the challenges that are, keeping it from being a magic bullet for every industry right now.
Okay, so let's start with that core ideology. You mentioned three foundational pillars. The sources seem to describe them as being in a kind of constant friction with each other, a balancing act that defines the whole industry. What are those three essential elements?
They are security, scalability, and decentralization. If you only remember three words about blockchain today, those are the ones.
Decentralization seems like the place to start. I
Yeah.
mean, it's the radical idea that really separates blockchain from, well, everything that came before.
Mm.
Can you explain why removing a central authority is so revolutionary?
Of course. Historically, trust has always required some kind of middleman, a bank, a government, a notary public. Decentralization it removes that need. The blockchain isn't stored on one single server or controlled by one company. Instead, it's maintained and verified by a huge global network of independent computers or nodes. They're all operating what's called a distributed ledger.
Distributed ledger.
Right. And that structure resists censorship and hacks because there's no single point of failure. If one computer goes down, tens of thousands of others are still running.
But doesn't that create a huge security problem? I mean, if no one is in charge, how do you know the information is actually correct? How do you know it hasn't been tampered with? And that brings us to pillar two, security. How does the network guarantee trust without that central person in charge?
This is where the math comes in. The security is achieved mainly through some really sophisticated cryptography. This involves a couple of major elements. First, you have hashing. That's the process that creates a unique, fixed string of characters for every piece of data. Then you have digital signatures, which verify who sent the data. And when you combine those with what are called consensus algorithms, well, you get what the sources call a trust mechanism.
So the mass is the trust.
Precisely. And the key outcome here is a concept called immutability. Once a record is put into a block, the cryptography makes it so computationally expensive to alter that one piece of data that it's essentially impossible. That immutability is the promise of fraud resistance.
Okay, so we have a decentralized system for resilience, and it's cryptographically secured for immutability. That leaves the third pillar, scalability. And this is where the tension starts to build, isn't it?
It is. It's the Achilles heel for many networks, and it's part of what people call the blockchain trilemma. The idea is you can have any two of the pillars, but getting all three is incredibly difficult.
I see.
So scalability is just the network's ability to handle a huge volume of transactions and to do it quickly and efficiently. But because you need all those independent computers to ensure decentralization and security, the process is extremely resource intensive and often pretty slow.
So if you want maximum security and decentralization, you usually have to give up speed.
That's the trade-off.
That makes perfect sense as a core conflict. So now that we understand those tensions, decentralization, security, and the scalability problem, let's look under the hood. Let's trace the life of a single record as it moves from being created to being permanently on the chain.
What's really fascinating here is just how rigorous the process is at every single stage. And it all starts with a simple intent to make a transfer.
Step one, transaction creation. So this is when someone decides to exchange an asset, right? Money, information, whatever. The record has the basic sender, recipient, the amount. But what makes this digital record trustworthy from the get-go?
The digital signature. When you create that transaction, you sign it cryptographically with your private key. And this signature proves two things to the whole network. First, that you're the one and only authorized owner who started it. And second, that the data in the transaction hasn't been changed at all since you signed it. It's the foundation of what's called non-repudiation.
Okay, so the transaction is signed and then is broadcast to the network,
Oh.
which takes us to step two, verification and validation.
Correct. The transaction goes into a sort of waiting room, a pool of pending transactions. Then all these independent nodes on the network have to check it. They confirm the signature is valid, that the sender actually has the assets to send, and that it all follows the network's rules. It's like a real-time audit done by everyone at once.
And only after that check does it move to step 3, where the data gets locked down. Block formation. This is where the chain part of blockchain really comes in.
Yes, and this is where it gets a little technical, but it's probably the most important part to understand. All those validated transactions are bundled together into a new block. The network then creates a unique ID for that block, the hash, by running all its contents through a mathematical function. But here's the brilliant part. The hash for this new block is calculated using not just the new transaction data, but also the hash of the block that came immediately before it.
Wait, hold on. So the new block contains a cryptographic reference to the old one, to
Exactly.
the block right before it.
And that link is the chain. If you try to go back and change one tiny detail in a block from last week, that change would instantly invalidate that block's original hash. And because every following block's hash depends on the one before it, the change would cascade forward, invalidating every single block after it.
Wow.
The network would just reject that whole sequence immediately. It guarantees immutability.
So that built independence is the security guarantee. It's a computationally verifiable audit trail. Okay, so finally we hit step 4, consensus and block addition. The whole network has to agree to finalize this new securely linked block.
That's right. The nodes have to reach a consensus, a collective agreement, that the new block is legitimate and should be added forever. This is where you hear about things like proof of work. Different consensus mechanisms determine how that agreement is reached. Once they agree, the block is committed and the ledger is updated across the entire network. The record is now permanent.
So we've covered the theory, the mechanics. It's a system designed to create trust through distribution and cryptographic certainty. It sounds like a solution for almost every data integrity problem we face today. So what does this all mean for the real world, beyond just digital currency? Let's shift our focus to the transformative potential the sources lay out.
The potential is just vast, because every industry needs trust and efficient records. Financial services is the most obvious place. Blockchain can get rid of the slow, expensive middlemen for things like cross-border payments. It provides a level of transparency that's just impossible with current banking ledgers. And it can automate contracts using what are called smart contracts.
The cost savings for sending money internationally alone are just staggering. But let's look at a totally different area, healthcare. How can this technology protect patient health and privacy?
In healthcare, the focus is really on solving data security and interoperability problems. Blockchain can enhance patient privacy while also improving data security. Specific applications include securely storing and sharing sensitive medical records between different hospitals, which is a huge challenge today. It can also improve clinical trials by timestamping data, and critically, it can stop fake medicines from entering the supply chain by creating a verifiable record of where they came from.
That real-time tracking, knowing exactly where a product came from and every hand it passed through, that's huge for supply chain management too, right?
Absolutely. The supply chain is a perfect fit. Blockchain provides this incredible transparency with that immutable record. It allows for real-time tracking of goods, it reduces counterfeiting of high-value products, and it helps ensure ethical sourcing. For example, you can prove that a diamond or a coffee bean came from a conflict-free zone.
And what about the public sector? I mean, governments often struggle with bureaucracy, data security, trust issues.
Here, the technology offers fundamental improvements in integrity. The sources talk about how it can enhance government operations with more security and transparency. You could improve the integrity of voting, for instance, or reduce fraud in public assistance programs. And you could securely store public records, replacing these old, cumbersome paper systems with a reliable digital ledger.
It paints this incredible picture of a fully efficient, transparent, trustworthy digital world. Which brings us to the necessary reality check. If blockchain is so promising and it's been around for over a decade, why isn't it running everything already? What are the difficulties and challenges holding it back?
There are some major hurdles, and we can go right back to that trilemma we talked about. Scalability is still the #1 problem for many of the biggest networks. The issue is sort of threefold. There's limited block size, there's network congestion when too many people are using it, and then there's the massive energy consumption of certain consensus mechanisms.
Let's focus on that energy consumption critique. That's the one most people have heard about, especially with proof-of-work systems.
Correct. Proof of work, or POW, is the process where computers compete using just raw computational power to solve a math problem to validate a block. It requires a vast amount of resources, which leads to very high energy consumption. It's great for security, but it has a really steep environmental cost.
Are there solutions in the works to fix that scalability and energy problem?
Oh, yes. The industry knows this is a huge issue. Solutions include just increasing the block size limits to pack more data in, but more importantly, people are developing alternative consensus mechanisms like those based on state instead of work that don't rely on that kind of brute force computation. There are also layer 2 solutions that process transactions off the main chain to reduce the load.
Okay, so moving away from the technical problems, what about the regulatory challenges? I mean, when you introduce a technology built on decentralization, it seems like it would instantly conflict with our centralized legal systems.
It's a major headwind for adoption. The regulatory challenges are, well, there's a serious lack of clarity all over the world. How do you apply know your customer laws to a network where users can be anonymous? How do you legally enforce a smart contract that just executes itself automatically? There are huge data privacy concerns, and regulators are trying to balance the risk of money laundering against the promise of transparency. It's a minefield.
Right. And then there's the final major challenge, which probably makes everything else even more complicated, a lack of standardization.
Yes. This is what's really limiting the technology's potential for big businesses. Different blockchain networks, one for finance, one for supply chains, they often run on completely different incompatible protocols. They just don't talk to each other well.
Hmm.
And creating common standards across this huge, competing, decentralized ecosystem is incredibly difficult.
We've covered a lot of ground today. We started with the immense potential built on those three pillars: decentralization, cryptographic security, and that elusive goal of scalability.
And that structure allows for these incredibly versatile use cases across finance, healthcare, government, basically offering verifiable trust without a human middleman.
But all that potential is hitting a wall of practical reality. You got the scalability and energy problems, a fragmented landscape because there are no standards.
And all of this is happening while regulatory bodies are just struggling to catch up. The sources really show a clear path to radical efficiency, but that path is full of technical friction and, frankly, political resistance.
So here is the final provocative thought for you to carry forward. If blockchain's greatest strength is the immutable, trustless record it provides, what happens when governments and regulators finally create the ironclad standards needed to define who is ultimately responsible for every piece of data on that record? Will the standardization required for mass adoption ultimately compromise the radical, untraceable decentralization that technology was originally built on? Something to mull over as you watch the next generation of these applications unfold.